Okay, so here is part 3 of 3, and I will print this for you. Okay, so you don't have to take notes, but just watch it and try to understand it. So absolute value functions, and the first example is taking a limit that involves an absolute value function. And when you're taking a limit, the first thing you try is direct substitution. So I substitute in 1, and I get 1 minus 1 over the absolute value of 1 minus 1. I get 0 over 0. Okay, and then I will say this. Okay, so all right, so now I know I can use L'Hopital's rule. So I will say, therefore, by L'Hopital's rule, the limit as x approaches 1, and then I'm going to do, I've never done this before, but let's write dt over db. Okay, means the derivative of the top over the derivative of the bottom. And this is equal to the limit as x approaches 1. Okay, the derivative of the top is 2x. And now the derivative of the bottom, the bottom is an absolute value function. So we have to do some work here. So let's say, let g of x equal the bottom. Okay. Then we're going to take x minus 1. And then we've got to split it up. The way you always want to handle an absolute value function is split it up into a piecewise function. So, so we got to take the input of the absolute value, which is x minus 1. Do a little number line. Where is this 0? It's 0 at 1. To the left of 1, for any number to the left of 1, this is negative. For any number to the right of 1, this is positive. So we have to negate this on the negative interval and keep it positive, keep it itself on the positive interval. So this is x, negative x plus 1, my bad, because I'm negating this. I'm negating this on the negative interval for x less than or equal to 1, and it's x minus 1 for x greater than 1. Okay, so if you do this, then, and I let g of x be the absolute value of x minus 1, then g prime of x, okay, which is, maybe I'll say here, that's the derivative of the bottom, is equal to the derivative of this part, of this piece is negative 1, the derivative of this piece is positive 1. Now, guys, you can kind of see that these parts, well, okay, let me not say that. What I'll say is I'm not putting or equal to at these, on either of these, because I don't know if the derivative even exists at I don't even know if the derivative exists at 1. I'm actually pretty sure it doesn't, because these are constant functions and they are not the same. So what we have to look at is the limit from the left of g prime and then the limit from the right eventually. So it looks like the derivative does not even exist there, because these are not going to be close to matching as you approach 1 from the left and right. So anyway, now that I've defined this derivative is g prime, I can go g prime of x, okay? And then, you know, we've got to figure out what this equals. But since g prime is piecewise, we have to consider the limit from the left and the limit from the right, because it's piecewise. The limit we're looking for is as x approaches that endpoint. So what I've got to do here is I've got to say the limit as x approaches 1 from the left of 2x over g prime of x is equal to the limit as x approaches 1 from the left of 2x over, if you're approaching 1 from the left, those are numbers like 0.9, 0.99, 0.999, 0.9999. So 1 from the left is this interval, so it's -1 is what that would be. Yeah, so we would be using this piece. And then you could just plug 1 in. So this ends up being 2 times 1, because now we're direct substituting. So the limit from the left of this is -2. And remember, if the left-hand limit and the right-hand limit are not equal, then that means the limit doesn't exist. So now we go the limit as x approaches 1 from the right, 2x over g prime of x equals the limit as x approaches 1 from the right, 2x over, okay, so approaching 1 from the right, that's like 1.1, 1.01, 1.0001, etc. So we would be on this interval. So it's going to be, so g prime of x on that interval is just 1. And we end up with 2 times 1 over 1, which is +2. Guys, the limit does not exist. So back up here, it does not exist. Okay, because of all of that. Okay, now here is a derivative example. So same as before, if you are dealing with an absolute value function, you need to express it piecewise. You need to rewrite it piecewise. So we're finding this time the derivative of this. So I want to express this piecewise. Okay, so you take the input of the absolute value function, and you've got to figure out where it's 0, so you should factor it if you can. So this is dots. Okay, so it's 0 at +3 and -3. Okay, now when you plug in values, plug them into the factored form, because then you just have to think about a negative times a positive, or a positive times a positive, or a, negative times a negative. So if you plug in like -5, like -5, you would get a positive and a negative. Positive times negative is negative. Plug in 0, you would get a positive times a positive, which is a positive. Plug in 5, positive, you'd get negative, positive, negative. Okay, so we need to negate this on the negative intervals and keep it the same on the positive interval. So it's going to be -9 plus x squared for x is less than -3. It's going to be this. And it's going to be this again. Okay, and I have to use less than or equals at the endpoints, but only for like one of the pieces. Like I don't want this and this to both be less than or equal, or this and this to both be less than or equal. Okay, so then okay, so I'm going to go like this. Actually, guys, I want to show you something, okay? So this is going to be, this will be illuminating, I think. Okay, so I want to graph, all right, so let me make sure I'm in a standard window. Okay, okay, so in a standard window, okay, let me graph 9 minus x squared. Okay, that's just the input. Okay, I'm graphing that in red, in blue. Okay, so this is the positive part. Okay, so see, like from here, we could see that this is the positive part, and then on these intervals, we got the negative parts. But then I go back to y equals. Now I'm going to do the absolute value of it, and that's going to be in red. Okay, and look at the difference. The positive part is the same, but then the parts that were negative get reflected over the, get flipped over the x-axis. Okay, and when you negate a function, it flips over the x-axis. So I just want to say to you real quick that the derivative graph, no, not the derivative graph. That y equals absolute value of 9 minus x squared looks like this. Whoops, oh crap, it looks awful. Looks like that. And guys, these are sharp corners. Okay, this is -3, this is 3. All right, those are sharp corners, and the derivative will not exist at these sharp corners. All right, any sharp corners, the derivative doesn't exist there. So I want to point that out first. So now we just take the derivative of each of these pieces. So d dx, absolute value of 9 minus x squared equals, okay, the derivative of this is 2x, the derivative of this is -2x, the derivative of this is 2x, and now we just got to do the intervals for x is less than -3, and then for x is greater than 3. And guys, the reason I'm not doing or equals to or equals anywhere is because the derivative does not exist at x equals plus or minus 3, all right, because you've got those sharp corners. As you can see, here, let me unhighlight this. There's the derivative graph. Okay, you can see, no, it's not the derivative graph. I keep saying that. There's the graph of the absolute value function that we're taking the derivative of. And these sharp corners mean that it doesn't have a derivative there. The derivative doesn't exist there. Sorry, I kept saying that wrong. Okay, now here, so here's an integral example, and the integrals are related to antiderivatives. So, and guys, it's the same situation. If you're dealing with an absolute value function, you need to split it up into a piecewise function. So I'm gonna go like this. And actually, this is legitimate notation, guys. In college, we would do this sometimes. So like, I'm gonna come back to this later. So right now I'm just gonna say equals star, so I don't have to like rewrite this. So this is equal to whatever star is, and then later I'll have star equals. Okay, so I take x to the third minus 5x squared plus 6x. Okay, and I want to make it a piecewise function. So I take it, and I've got to figure out where it's positive or negative. So first I factor it. X minus 2, x minus 3. Okay. So we've got 0, 2, and 3. Pick some number over here. I'll pick -5. Okay? Plugging in -5 would give me a negative, and a negative. Negative times a negative times a negative is a negative. I could plug in 1. That gives me a positive times a negative times a negative, which would be positive. I plug in 2.5. Positive, positive, negative. So negative. I plug in 5. Positive, positive, positive. Okay. So I'm going to negate. Oh, yeah, actually, let me show you another. I think that this is a good visual. All right, so here is the original function. Let's see if this works. X to the third, not the original, but the input. Sorry, I keep misspeaking. I'm tired. Okay, so here is, all right, so that'll be the input, and then this will be the absolute value with the input. All right, I thought I could copy and paste for a second. X to the third. 6x. Okay. So the input itself will be blue, and then the absolute value function we're working with will be red. I hope it shows up. Okay, there's the blue. And then look at the red. So the positive, oh, okay. So these positive parts, so right here and right here, we have the same graph as the input. But then the negative parts, which are below the x-axis, they flip over the x-axis. That's why they get negated. Okay, so hopefully that helps you understand this better. So I have to negate the input on this interval, keep it the same here, negate it here, keep it the same there. So negative x to the third x squared minus 6x. All right, and then keep it, negate it. Okay, this interval, x is less than 0. This interval, 0. This I did less than, so I got to do less than or equals to on the next one. And I guess I'll just do less than 2. All right, 2. And since I did less than here, I've got to do less than or equals to here. 3. And since I did less than there, I got to do greater than or equal to there. Okay. And now, so to take the integral of this, the area, to find the area under this curve on 0 to 4, we've got to split it up into different integrals. Now this integral starts at 0. So this part that is less than 0, we don't need. All right, and so down here, so I'm going to take this star, and I'm going to put it here. This is just a nice way for people to follow your work. The integral from 0 to 2, x to the third, plus the integral from 2 to 3, and this is a negative part, plus the integral from 3 to 4. An eraser minus 5x squared plus 6x. Okay, now guys, from here, you would only need to even do this if it was a no calculator section, because if it were a calculator section, you could have just used Math 9 from the beginning. So since we're sort of assuming that this is a non-calculator problem, we need to use the fundamental theorem of calculus down here, and we've got to use it on 3 separate integrals. So we'll just set it up and do the antiderivative part, and then I'll just tell you what the answer is. Okay, yep. And then what goes in here is the antiderivative. So it's a 4th x to the 4th plus, okay? Oh, and by the way, the same input is also over here. So it's going to have the same antiderivative. So let me just put it in already. And then this one here is just going to really have different signs. Ah, 3. Okay, and then you'd plug in 2 and then subtract what you get when you plug in 0. So plug in top minus plug in bottom. Plug in top minus plug in bottom. Plug in top minus plug in bottom. And then, of course, you're adding it all together. So this is the, we'll just say here, that's the FTC, the fundamental theorem of calculus, and then 37/6. Okay, but again, you would not have to do any of this if it were a calculator section. You could just use Math 9. Okay, so there's that.